All right then. Well, 3-1 and 3-2 took a long time, so we'll see what happens with 3-3. It's not as much material, and we'll see what we can talk about in the next, I don't know, 7 or 8 minutes or so. We're still looking at neutral geometry. Venema's section 3.3 talks about plane separation. It brings in the fourth of 6 axioms we're going to take a look at as we're building a neutral geometry. Neutral geometry meaning it doesn't give a rip about Euclid's parallel postulate. Don't know why anybody does. So here's axiom 4. For every line L, the points that do not lie on L form two disjoint non-empty sets H1 and H2 called half-planes bounded by L, such that the following conditions are satisfied. First, each of H1 and H2 is convex. Second, if P is in H1 and Q is in H2, then segment PQ intersects L. So, talk about a couple things here. We should talk about what we mean by convex. What do we mean by convex? Well, we mean that anytime you draw a line segment from a point in the plane, in the set, to another point in the set, that segment is completely contained in the set. So if I draw some figure like this, we say that it is convex because no matter which 2 points I connect in the set, that segment is contained completely in the set. But this is not convex because if I try to connect this point to this point, that segment will not be entirely contained within the set. So you have convex and not convex. Convex on the top, not convex on the bottom. This is not a surprising axiom. It's quite intuitive. I take some line. I've got H1 up here and H2 down there. Those are half planes. We imagine that the line divides infinity into 2 infinitely big half planes. Let's not even think about that. If I have some point P and it's in half plane 1 and some point Q and it's in half plane 2, then the segment between them must intersect line L. Must. Okay? Little bit of notation, little bit of definitional stuff. We say that P and Q are on opposite sides of line L. We say that they are on opposite sides of line L, as opposed to being on the same side. So we'll say that P and R are on the same side of line L. And when we say same side, we mean that segment PR does not intersect L. Q and R are on opposite sides because segment QR does intersect L. Okay? Okay. So one other big idea we should probably talk about. We should talk about angle. Now, it's a bit of a hand-wavy definition. It just is. So I take a ray. Now remember, a ray, let's call this ray AB. Ray AB is segment AB, and then all those points P such that B is between A and P. So it's all of those. If I take any other ray that starts at A and is not opposite to AB, the opposite ray would go that way, you'd get a line. I take any other ray, ray AC, for example, I get an angle, the angle being the union of 2 non-opposite rays. And you get the same general definitions that you do from high school. A is called the vertex. The rays are called the sides. This space in here is called the interior. You could, oh, let's go purple with that. Because if we pretend that ray AB divides things into two half planes, and ray AC divides the plane into two half planes, then the red-blue, what really should be purple area, is the interior. This is the interior of angle CAB. That's interior. The interior of an angle is convex because I can draw a segment from any point in the interior to any point in the interior while staying completely in the interior. This notion gives us an opportunity to talk about what we mean when we say that this ray is between rays AC and AB. To say that ray AD is between AC and AB, we mean that it lies in the interior of angle CAB. Okay? Okay. Okay. So we're doing all right. Oh, we should also probably talk about this thing. We should talk about that. Venema gives a very interesting definition for triangle. Very interesting because triangle means that it has three angles, but he defines a triangle to consist of the union of three segments. Segment AB, union segment BC, union segment AC, and he defines triangles to be non-degenerate triangles, which means that A, B, and C cannot be collinear. So we would say that triangle ABC is the union of three line segments. Now you get three angles as a result, but to define a triangle in terms of its sides is a bit weird. Okay, one more thing in this section that we should talk about. Pasch's axiom. This is not actually an axiom, it's a theorem, but it's called an axiom because it's in his foundations of geometry. When he built a geometry, he built this in as an axiom. It's actually not hard to prove using the axioms that we've laid down, and so that's what we're going to do. We're going to let triangle ABC exist, and we're going to let L be a line such that none of A, B, and C lies on L. If L intersects segment AB, then L also intersects either AC or BC, not both. Either AC or BC, not both. So just so we're clear on what this looks like. So you have some triangle. Oh, that's ugly. You have some triangle, looks like this, and L is going to be a line such that none of the vertices of triangle ABC are on the line, and L has to intersect segment AB. So does L intersect AC or BC? Not both. And this boils down to A is up here in half plane H1, and B is down there in half plane H2. A and B are on opposite sides of line L because line L intersects segment AB. The question is, where is C? Well, C has to be either in H1 if I drew my diagram badly, or in H2 if I drew my diagram well. If C is in H2 as it appears, then A and C are on opposite sides of line L, and you get the intersection that you need. If C is in half plane H1, counterintuitive based on the picture, then segment BC must intersect line L. So this is one of those things that's you think it's obvious, but you do actually have to think about why this is true. You have to build yourself a geometry, and things that are intuitively obvious may not necessarily be intuitively obvious. All right, so that's good for now. That's section 3.3, at least the stuff I'd like you to come to class having seen, and we'll talk and play when we get there, and there it is. Thanks, everybody.